Hello, this is Dr. Joe Trout from the physics program at Stockton University. And this is chapter 20. Right, if we look at this image, it's taken by the Hubble Space Telescope, and it shows a young star cluster interacting with a cloud of gas from which it was recently formed. So the bright blue stars of the cluster have blown a bubble in the gas cloud, and the remains of this cloud can be seen in the lower right hand part of the frame. And the glowing is in response to the starlight illuminating it. So in its darkest parts, shielded from the harsh light, the new stars continued to form. And although the star formed only recently, the most massive of them are already dying and ejecting their mass and producing the blue ring and the streak features that are visible in the upper left-hand corner. So thus the image shows the full cycle of life of a star, the formation of the interstellar gas through the life of the main sequence and to the death and the return of stellar matter to interstellar space. So there's various types of interstellar matter. So here we see this reddish nebula and the photographs glow with light that's emitted by hydrogen atoms. So the hydrogen atoms absorb energy, their electrons move to further orbits, and then they decay back down to their lowest energy and emit light. So the darkest area of the clouds of dust are clouds of dust that block the light from the stars behind them. And the upper part of the picture is filled with like a bluish glow of light. And it's reflected from the hot stars embedded in the outskirts of this huge, cool cloud of dust and gas. So the cool supergiant star Antares, it can be seen as a big reddish patch in the lower left part of the picture. And this star is shedding some of its outermost atmosphere, and it's surrounded by this cloud of its own making. And it reflects red because it reflects the red light of the star. The red nebula in the middle part, right portion, surrounds the star. If we look at the Orion Nebula, we have the red glow that pervades the Great Orion Nebula is produced by the first line in the Balmer series of hydrogen. So the hydrogen emission indicates that there are hot young stars nearby that actually ionize the clouds of dust. If you remember, we said ionized means that we're taking off electrons from the atom. So when the electrons then try to recombine with the proton and move back down to lower energy level orbits, then emission lines are produced. So this is what produces the red color. The blue color, seen at the edges of some of the clouds, is produced by small particles of dust that actually scatter the light, much like particles of dust in our atmosphere scatter the blue light and make the sky blue. So this is what happens. We're on the Earth and we're observing a star, and what we get is the spectrum to the right. And we see these narrow absorption lines. But what's really coming from the star, due to the hydrogen, are these broad absorption lines. So as the light moves through this interstellar dust cloud, it excites electrons, and then the electrons move back down to their orbit and emit light. So they absorb some of the light that's going through. So if we look at the absorption lines through this interstellar dust cloud, when there's a significant amount of cool interstellar gas matter, which is gas with some dust, between us and the stars, we can see the absorption line of the gas in the star's spectrum. And we can distinguish the two kinds of lines, whereas the star's lines are broad, the lines from the gas are narrower. Now we talked about the atoms going from moving up to higher energy orbits and then decaying back to their lower energy orbits and emitting a photon. But this didn't explain all of the spectral lines that we were seeing. So what we also know is that if we look at a hydrogen atom and we see there's a proton and an electron, and they're both also spinning, much like the Earth spins around its axis. Or at least that's the picture you can put in your head. So if they're both spinning in the same direction, then we say, for instance, that their orbits are aligned, but also the electron can spin in the opposite direction. So in that case, we either have A, the orbits are parallel, or B, the orbits are anti-parallel. So when an electron in a hydrogen atom is closest to the nucleus, the proton and electron may be either spinning in the same direction or the opposite direction. And when the electron flips over, the atom gains or loses a tiny bit of energy by absorbing or emitting energy with a wavelength of 21 centimeters. So this explained one of the lines that we were seeing. So Howard Ewan and Edward Purcell, we see Howard in 1952 working on a horn antenna, right, at the top of a physics lab in Harvard, and it made the first detection of this interstellar 21 centimeter radiation. So if we look at this Vela supernova remnant, about 11,000 years ago, a dying star in the constellation Vela exploded, becoming as bright as the full moon on the Earth's skies. And you see a faint surrounding filaments from the exploding of the center of these colorful images. And if we look at the edges of the remnants, they're colliding in the interstellar medium, heating the gas that they're plowing through to temperatures of millions of Kelvin. So this is really hot. So the telescopes in space also reveal a glowing sphere of X-ray radiation from the remnant. So most of this matter and a lot of the gas that we're seeing is just helium and hydrogen, in fact at a really low density, much lower than we see on Earth. In fact, much lower than any of our vacuums on Earth. But sometimes we do also see molecules that are more complex that consist of many atoms. And this is a three-dimensional perspective. It shows the characteristic cage arrangement of a 60 carbon atom in a molecule of fullerene C60. This is known as a buckyball, and its full name is Buckminster fullerene, because of its similarity to the multi-sided architectural domes designed by the American inventor R. Buckminster Fuller. Here we see an unusual picture. What we see is this object that was first cataloged by Barnard is a dark interstellar cloud, and its striking appearance is due to the fact that since it is relatively close to the Earth, there's no bright stars between us and its dust actually obscure the light. So what we're seeing is actually what we can't see, right? So it's a dark cloud that actually is so thick that it it obscures all the light that's reaching Earth. So Barnard observations provided information that furthered many astronomical observations. So one way we can look at this dust and this dust once again is what forms the stars and the planets, right? This is visible in infrared images of the Horsehead Nebula in Orion, and that was just a horrendous bolt of lightning, in case you've heard some noise in the background. And this dark cloud is one of the, because it's raining outside, so this dark cloud is one of the best known images in astronomy, probably because it really does resemble a horse's head. Right. So now we can see the infrared images of the planes of the Milky Way. And if you remember, infrared is pretty much, it's the wavelengths of electromagnetic waves that are just below red, right? And you pretty much think of them as heat. So this image was taken by the Spitzer Space Telescope, and it shows a field in the plane of the Milky Way. Right, so our galaxy is the shape of a frisbee roughly, and the plane of the Milky Way is a flat disk of the frisbee. So since the Sun, Earth, and solar systems are located in the plane of the Milky Way at large distances from a center, we view the galaxy from the edge on, so it's like looking at the edge of the frisbee. And much of what we look at looks like glass plate to the end. So the image is produced by tiny dust grains which emit at 3.6 microns in the blue image and 8.0 microns in the green image and 24 microns in the red image. And the densest region of the clouds are so cold and opaque that they appear as dark clouds even at these infrared wavelengths, right? So we see no heat from them. The red bubbles are visible to indicate regions where the dust has been warmed by young stars that are nearby. If we look at this star cluster, the bluish light surrounding the stars in this image is an example of reflection nebula. So like fogs around the street lamp, right? If you ever looked at a light through fog, you'll see that there's a cloud around it. And what we're seeing is a reflection of nebula shines only because the dust within it scatters light from a nearby bright source. So this cluster is currently passing through the interstellar cloud that contains dust grains which scatter the light from the hot blue stars in the cluster. Once again, if we look at the infrared image, this is Barnard 68, and in this image we see Barnard 68 is the same objects shown in a previous figure, and the difference is that, and remember that figure showed a dark cloud where we just couldn't see through it, so it showed up as black. The difference from the previous image is that the blue, green, and red channels showed light in the visible or very near visible part of the spectrum. In this image, the red color shows the radiation emitted in the infrared, so just below red, and at a wavelength of 2.2 microns. And the interstellar extinction is much smaller at the infrared, and so the stars behind the clouds become visible. So if we look at the scattered light by the disk, if we're on Earth, what we're going to see is that the interstellar light dust scatters blue light more efficiently than red light, just like our atmosphere, and therefore making the distant stars appear redder and give clouds of dust near the stars a blue hue. And here a red ray of light from the star comes through to the observer, whereas the blue light is scattered to the sides. And once again, this is similar to what happens in our atmosphere, giving our sky a blue look, right? And finally, what does these models of these interstellar dust? So typically, this interstellar grain is thought to be consist of a core of rocky materials such as silicates or graphite, surrounded by a mantle of ice. And typically, the sizes are from 10 to the minus 8 to 10 to the minus 7 um, microns, or meters, excuse me. So this is about almost a nanometer, right? So almost as small as a nanometer. All right, so it's this dust and gas that's going to form the stars that we'll see in the next couple of chapters. Okay, so thank you.